All right, so continuing on from our previous situation, we're going to do another example and then one more. And then afterwards, I will be able to introduce you guys to an application of second order differential equations. And what we're going to study is mechanical vibrations. Okay. And after we finish mechanical vibrations, we're going to move into Laplace transformations. And then after we move into Laplace transformations, just to give you a sneak preview, then we're going to start moving into linear algebra and differential equations and combining those two so you can finally see how those two combine and come together to solve very large systems of differential equations. Okay, so let's go ahead and get started with our second example. Okay, so for this example, we're going to find a general solution okay, to the following differential equation. Okay, and that differential equation is going to be y double prime minus 2y prime, okay, plus y equals e to the t, okay, divided by t squared plus 1. Okay, so first we need to find the complementary solution for this differential equation. So again, I will leave it to you to verify the complementary solution and to find it. For this problem, the complementary solution is found to be c1 e to the t, okay, plus c2 t times e to the t, okay? So we have y1 of t, which is going to equal e to the t, okay? And y2 of t, which is going to equal t e to the t, okay? So therefore, the Wronskian go ahead and spell that better. Okay, the Wronskian of these two functions is w, which equals the determinant, e to the t, and then the derivative of e to the t is e to the t. And then we have t e to the t, and then using the product rule, we end up with e to the t plus t e to the t, just like that. Okay. And we are taking the discriminant, or excuse me, the determinant. And this is going to equal e to the t times e to the t plus t e to the t, okay, minus e to the t multiplied by t e to the t. And if you compute this correctly, this will simplify to be e to the 2t, just like that. Okay. So now the particular solution can be okay, is then y, capital P of t, okay, and this is going to equal negative e to the t, that's our y1, multiplied to the integral of t e to the t times e to the t, okay, all divided by e to the 2t, okay, times t squared plus 1 dt, okay, plus, and this will be t e to the t, that was our y2, integral, and this is going to be e to the t times e to the t, all divided by e to the 2t, okay, times t squared plus 1, all right, all with respect to t. All right, and we can simplify this. This will simplify to become minus e to the t integral t divided by, and this is going to be t squared plus 1 dt, okay, and plus t e to the t, okay, times the integral of 1 over t squared plus 1 dt, okay, and if we can simplify this one more time by solving the integrals, we end up with the following. We get minus 1/2 e to the t as such times the natural log of 1 plus t squared, like this, plus t e to the t times inverse tangent of t. Okay, and so at one point in class, several of you have asked me, can we use an integral calculator to do some of these to perform some of these integrals? The answer will always be yes in my class. Okay, I do not expect you guys to memorize or to bring a table of integrals so that you can do this type of calculation or computation. Software has been built specifically to make our lives easier, so feel free to use any integral software out there to help you obtain these solutions. Okay, so this is the final answer, and therefore the general solution is y of t, which is going to equal the complementary solution, c1, e to the t, plus c2, t e to the t, okay, and then minus the particular solution, which would be minus 1/2 e to the t times the natural log of 1 plus t squared, okay, plus t e to the t times inverse tangent of t. Okay, and that is the answer This is the general solution for the differential equation for this example. All right, so in our next video, we'll do one more example, then we'll move on to mechanical vibrations.